So this part is optional. We want to give you a little bit of understanding of proofs of Green's theorem and so how this thing works. And what we start with is we kind of prove the Green's theorem over a rectangular region, and then we extend that to a rectilinear regions, which means that they're a region that has all it can be divided into rectangles, and then we do something funky with that. The same thing that we did with Riemann sums, and similar things that we did with Riemann sums, that happens with those rectilinear regions. Now, so we start case one, rectangles, and let's say f is p and f is x component p, y component q, and the region is AB times CD, and there are four curves that make the boundaries, and basically four lines that make the boundary: S, E, N, and W. And so any the contour integral f dot dr is going to be basically the contour integral, and it's going to be the line integral over S, the vector line integral over E, vector line integral over N, and vector line integral over W, all added together. Remember, on S, dy is 0, on N also, on E and W, dx is 0. And then you can see any parameterization of S is going to have a C constant, and then X is going to run from, now I can have the simplest parameterization that it's X and C, and it goes from A to, X goes from A to B. Similarly, with all those pieces, you can parameterize them with just either X goes between something and something, or Y goes between something and something, and the other component is going to be a constant. And so now we use those to write down each one of these line integrals. And so it turns out, and if the Y component is constant, then you only have the X component working out for you. And so you get f, the X component of f dx, basically. And that's why we have f dot I. And then for the second part, you only have the Y component is going to work. So it's f dot j. And then again, the third component on the upper side of the rectangle, it's f dot I, and the very left side of the rectangle is going to be f dot j. And so when you're computing these integrals, then we do something funky with it. We actually add up the two that have j in it, and add up the two that have I in them. But remember, the ones that have j in them, see the boundary is reversed. So you make the boundary the right way, putting the lower one down, the smaller one down, and upper one high, and this one's boundary becomes this integral becomes negative of it. When you switch the boundary, you have to multiply by a negative for that one, and same over here, these two. And so one of them you switch with a negative sign. Now it looks a little bit different, right? And so what you realize is that you're basically going, if f was p and q, the left integral is q of by minus q of ay, and the right integral is p of x and c and p of x and d. Oh, wait a minute, what could that be? Oh, that I can write this these two as integral of the derivative by fundamental theorem, right? I can write this as integral of derivative when over x, when x goes between a and b. So that's what we do. And so that's what happens. And then the other one, you write that as the derivative with respect to y of p, and where y goes from, let's see, c to d. And then if you write c to d, because this is d to c, you have to have a negative sign in here. This looks very familiar. Now put the two double integrals together, and by switch the order of this, like switch these two and then put them together, and you get the integral over the same boundary of qx minus py. And this is we just shown the proof that Green's theorem works for any rectangular region. Now the next discussion is supposed to help you understand why it works in the regions that can be broken down into rectangular regions. Now let's discuss rectilinear regions. And so if I want to prove this theorem for those type of regions, first of all, the double integral breaks down immediately, and we can see it immediately because the double integral over such region is going to be the summation of the double integrals over each rectangles. So that's the easy one to see. The next part is to show that the line integral is going to break down into those regions as well. And it turns out if I write it, it can be done like that. But right now I see that the boundary of D only has these pieces, but wait, if I do boundary with D1 and boundary D2 and boundary D3, there are extra pieces. But then the interesting part is that when you're basically going counterclockwise on D1, then you're counteracting the line integral on D3. In D1, this piece that is in common goes to, from left to right. In D3, it goes from right to left. So they're going to be negative of each other. So the inner part of the boundaries of D1, D2, D3 are going to counteract each other. And then, yes, you can write it like that. Even though it seems like there are more, we're adding more pieces of boundaries to this, and those are the inner one. But inner ones counteract each other, and so you basically prove that the integral over the boundary D over here is going to be summation of the integrals over the line integrals over the boundaries on the right. And so so what do we do with the general region now? Now that we have everything, if we can break it down into rectangles, what do we do with the general region? Basically, the general region becomes a limit of you can break down any general region, and we're going to come back to that, into rectangular regions basically, and then we find limiting, and when there are when we get them smaller and smaller, then basically it's going to cover the entire region, and that's the concept again, that those sums that are infinite sums, and the rectangles are going to get smaller and smaller, and it gives us the answer. Now, I click here 17.1.b. Evaluate this contour integral where C is oriented curve shown to the right. And so stop and we come back. Okay, so one way is to do the basically parameterize each piece. So that this one way is to use this and then divide it into 3 pieces, into C1, that entire thing, plus C2, which C1 is this, C2 is this, C3 is this, and parameterize the line segment and figure out the integral and compute. It seems very lengthy, so I'm going to use Green's theorem instead. Green's theorem. And so with Green's theorem, this is Q, this is P, Q and P. I have to do double integral over the region. Let's say d of q with respect to x, which is giving you y, and then p with respect to y, which gives you 0 dA. And that is the double integral over this region. And so let's say I want the inner one to be in the x direction, and then I will have integral 0 to 1 minus y, 0 to 1, and then y dx dy, and that is going to be 0 to 1, and we get y times x, 0 to 1 minus y dy, and then that would be integral 0 to 1, y times 1 minus y, which is y minus y squared dy, and this is y squared divided by 2 minus y to the third divided by 3, 0 to 1, 1/2 minus 1/3, that is 1/6, and that's the answer.